Okay, we're now continuing example 7 on page 34. It says, for any complex numbers Z1 and Z2, show that modulus of Z1 plus Z2 squared plus modulus of Z1 minus Z2 squared equals 2 times, bracket, modulus of Z1 squared plus modulus of Z2 squared. Now, we really need to go back, you need to go back to page 25 of your notes, and you will see that there is a result that the modulus of a complex number squared is equal to the complex number times the conjugate of the complex number. So that's from page 25. So you know Z is x plus, so I'm just going to do the result back here. Just note that this is a result that we looked at, a special result. Modulus of Z squared equals Z times Z conjugate of Z. Because isn't that x plus yi times what? X minus yi, which is x squared plus xyi, no, minus xyi plus xyi, what?
X squared plus y squared.
So that's x squared plus y squared if you expand it. Now, isn't that therefore the square root of x squared plus y squared all squared? Now, the square root of x squared plus y squared is the modulus of z, and then we're squaring it. So we know that the definition for modulus of z, just absolute value z, that one, looks like absolute value z, is the square root of x squared plus y squared. So modulus of z squared is the square root of x squared plus y squared squared. The squared and the square root cancel and you're left with x squared plus y squared. So we're going to use that result, otherwise it's going to get very big and complicated. Okay, let's go. So it says for any complex numbers, those two, show that result. I'm not going to say it again. So here we go, I'm going to start. Modulus of z1 plus z2 squared plus the modulus of z minus z1 minus z2 squared is equal to. Now, modulus of a complex number squared, we're going to use this result here, is z times complex conjugate of z. So this z1 plus z2 is the z. See, the rule is modulus of that squared. So I go, well, it's this complex number times its complex conjugate. I don't know what the complex conjugate of it is. Plus, the next one would be z1 minus z2 times the complex conjugate of whatever z1 minus z2 is. So I'm just pretending that that's a z squared is z times z bar. See, I've written exactly the same thing, z times z bar plus this, whatever it is, times z bar. Can simplify these. So that is z1 plus z2. I believe in the first exercise you looked at the sum, the conjugate of the sum equals the sum of the individual conjugates. So that actually can be written as z1 bar plus z2 bar. Plus, same thing here. The z1 minus z2 stays the same. If you do the complex conjugate of the addition of the subtraction of z1 and z2, you will get the same result for as complex conjugate of z1 minus complex conjugate of z2. Now I can prove that to you by just making up two complex numbers. All right? We've already done it, but we can do it. So if I say do 3 plus 4i plus 3, some other complex number, plus 2 plus 5i or something. So let's just try, I'll just get another piece of paper. Oh, we'll try it. What's this? Yeah, I think you've been asked to prove it, but you do it with x's and...
Yeah, they gave us two complex numbers.
Yeah. Look, I'll show... For example, 3 plus 4i and 2 plus 5i, for example. So let's do z1. So let's do, if that's z1 and that's z2, let's do z1 plus z2, its modulus. So what's Z1 plus Z2? 5 plus 9i. So it's the modulus of that, which is 5 minus 9i. Not the modulus, complex conjugate of that, 5 minus 9i. But if I just do the complex conjugate of each one first, Z1 bar is 3 minus 4i, Z2 bar is 2 minus 5i. If I now add them, I still get the same answer. That's what that result is.
So that's why you cannot take it as a negative.
So you can break it up. And that's why you can't take it as a negative. Notice that the x's are the same. So remember, complex conjugate just changes the y. It's the reflection in the x-axis. One's x plus yi, the other one's x minus yi. Different to minus z, your complex number.
minus
The
z is-
negative
Wouldn't it be negative?
is a
minus
rotation. It's I squared is negative 1. It's rotating 90 degrees, 90 degrees.
So if you did Z1 minus Z2 and you changed it, would it be negative 3 plus 4i? Like, would there be a negative?
Z1 minus Z2 would be 3 plus 4i minus bracket 2 plus 5i.
So you'd be changing the number, and that's why we can't do it for.
Yeah, negative Z is different to Z bar, totally different.
Yeah.
Yeah. All right, do you see the result? So basically it's saying you can just add them together and do the complex conjugate, or you can do the complex conjugate of each one first and then add them together. Same with the subtraction process. That's what we've said. We keep. So now we can expand this, but be very careful. This is Z1 times Z1 bar plus Z1 times Z2 bar plus Z2 times Z1 bar plus Z2 times Z2 bar plus Z1 times Z1 bar minus Z1 times Z2 bar minus Z2 times Z1 bar plus Z2 times Z2 bar. I better move this along. So I've expanded using the FOIL method for each one. And I believe a few things can cancel. Z2 times Z2 bar, no, which one's cancelled? Z2, Z1 bar, Z2, Z1 bar minus Z2, Z, that one with this one, and Z1 bar, Z1 times Z2 bar, that cancels with this. And then we've got a double up of Z1, Z1 bar plus Z1, Z1 bar is, we've got two lots of Z1, Z1 bar plus again the double up of the Z2, Z2 bars plus two lots of Z2, Z2 bar, which is a common factor of 2 bracket Z1, Z1 bar plus Z2, Z2 bar. They should look familiar. Look up the rule. Z times Z bar is Z, modulus of Z squared. Well, yeah. So therefore replacing that with modulus of Z1 squared plus this is modulus of Z2 squared. Done. We're done. I'm going to draw the number plane over here. O. I'm going to draw, if this is, for example, Z2, I'm going to have that represented by my vector OB. And if Z1 is represented by vector OA, wait, you can't see it. So, interpreting this geometrically. Here I've got vector Z1 and there I've got vector Z2. We know using the parallelogram method that this bit here is Z1 plus Z2, remember? So if that's Z1 and that's Z2, this will be Z1 plus Z2, that one like that. Oh, I should have drawn it outside because I'm going to cross the other one over. 1 minute. Z2. And I want to work out, see how we've got a Z1 minus Z2? So here we've got, look, see, I'm trying to represent everything here in this diagram. Here's a Z1 plus Z2, I've got it. I've got a Z1 here on its own. I've got a Z2 there on its own. But I don't have a Z1 minus Z2, so I want to draw that one in. We know that it's it's the other diagonal, but you've got to work out which way. So I'm just going to draw the other diagonal. You can work out which way it is. If I draw Z2 down here, we want Z1 minus Z2, don't we? So which way is Z1 minus Z2? Is it upwards or is it downwards? So let me draw minus Z2 down here, and there's Z1. If I completed the parallelogram, wouldn't it go, it's the downward one. So therefore, that one that way is, so the other one is Z1. This one is Z1 minus Z2. And you know what the other way is now, don't you? It's Z2 minus Z1 the other way.
Can you just pause it for a second? How did it go from?
If we want to do Z1 minus Z2, that Z1 minus Z2 would come down like this. Drawing up the resultant parallelogram, I've got that bit there, minus Z2 there. The resultant Z1 minus Z2 is that. But if I actually want to draw it inside the parallelogram, I'd put it there. It's that diagonal. Okay? It's 2. So if you do Z1 plus Z2 physics method, you end up on the right point. Same with parallelogram method. That point does represent the complex number. If we added them together, you would. But with the minus, you need to do Z1 minus Z2. This is actually the point representing Z1 minus Z2. But in the parallelogram drawn, that's the same vector as that. That's the actual position vector. That's the free vector. That's the true value of the complex number down here.
Does the vectors really mention anything?
If, now this is our interpretation, if you let the vector OA equal your complex number Z, and if you let the vector OB, so OA is, your complex number Z1, and if OB is your complex number Z2, then if you, by completing the parallelogram, and the parallelogram is OA, I'll call this point C. By completing the parallelogram OACB, then we can say that the vector OC equals what? Vector OC is Z1 plus Z2. Yeah, it is OA plus OB, but we know it's Z1 plus Z2. And we know that the vector BA, we just worked it out, was Z1 minus Z2. Now, why aren't I doing this point D down here? Because we're just interpreting this geometrically inside this parallelogram up here. All right? So we know that the vector OC is Z1 plus Z2. The vector BA is Z1 minus Z2. Why am I doing this? Because I have to interpret all this. Z1 plus Z2 modulus of that squared plus modulus of that squared equals 2 times modulus of Z1 squared plus modulus of Z2 squared. So, therefore, this is the result. Z1 plus Z2 squared, I'm just copying what's on top of the page, plus Z1 minus Z2 squared equals 2 times, bracket, modulus of Z1 squared plus modulus of Z2 squared. What does that represent? Let's just replace each one with what they are. What's Z1 plus Z2? Isn't it OC? OC
Plus BA.
Well, squared plus, this is BA squared equals 2 times OA squared plus OB squared. Now, in other words, I'm going to get rid of these vectors things now. So isn't that, wait a sec. Okay. Look at this parallelogram. Doesn't OA equal BC?
Yeah.
And doesn't OB equal AC? So, instead of 2 times all of that, I'm going to get rid of the vectors now. OC squared plus BA squared. Remember, sorry, I should not put the vectors there because you know what the modulus is? It's just the lengths. Remember the modulus is the lengths?
Yeah.
So I shouldn't really put those vectors there, all right? Modulus means the length of. So therefore, OC squared plus BA squared is equal to, we've got 2 times bracket OA squared plus OB squared, but I know that OA equals BC. So why don't I just say that it's OA squared plus BC squared plus instead of two lots of OB, why don't I just do OB squared plus AC squared? I know this is a bit out there. So instead of saying it's 2 times the length of this plus 2 times the length of that, I'm going to say it's the length of this plus the length of this plus the length of this plus the length of that. So I'm stopping. What's this telling me? The sum of the lengths of the diagonals, the sum of the squares of the lengths of the diagonals equals the sum of the squares of the sides.
Is that true?
It is. So therefore, the sum of the squares of the diagonals, now they might say, by doing this, show that the sum of the squares of the diagonals equals the sum of the squares of the sides. They can't just let you blindly walk in the dark. So the sum of the squares of a parallelogram equals the sum of the squares of its sides. Well, look at OC squared plus BA squared. Aren't they the two diagonals? So if you add the two diagonals, all right, I could say it's 2 lots of OA of one side squared plus the other side squared, but what's a nicer result? OA equals BC, opposite sides of a parallelogram are equal, and OB equals AC, so it's nicer to say that the sum of the diagonals squared equals the sum of the lengths of the sides that have been squared. Instead of saying 2 lots of OA squared, I've said, well, OA squared plus BC squared. And instead of saying OB squared, I've said OB squared plus AC squared because they're the same length. It just makes it sound like a nice theorem. Construction of the vector product of two complex numbers, that's what we're doing. So let Z1 and Z2 be represented by OA and OB respectively. So I'm just going to draw OA over here. Doesn't matter where I draw it, but we do tend to make A less than the B. So that's OA, and I'm going to put, say, OB here somewhere. I'm putting them strategically there for a reason because I don't want to go over the line. One sec. Actually, a bit too big. So OA, I'm just going to put OB here. So this is Z1, and this will be Z2. Okay, Z1 and Z2. Construct, so this is what they want us to do. Let I have coordinates 1, 0. So I'm just going to put it about here. Oh, maybe a bit lower. Let I have coordinates 1, 0. So this is the point I. And construct, we have to construct triangle OBM similar to triangle OIA. So I'm going to construct triangle OIA like this. Okay. All right. So this is triangle OIA. I'm just going to put that this here is an obtuse angle. All right. And there's A up there. Okay. So construct triangle OBM similar to triangle OIA. So why don't we just come out here for some obtuse angle there, and let's make this angle equal to that one. Now, so if I've made it similar to that, then this angle would have to equal this one, and I've got an angle here. I'm going to let that equal that one. Okay?
What gave you the information that it was an obtuse? Like there was an obtuse?
I can draw it obtuse or acute, but if I draw it acute, I'm going to come across here and I'm going to really mess up a lot of the space. So that's why I've done it obtuse. Okay? So it says let vector OM represent complex number Z sub 3. That's Z sub 1, Z sub 2, That one's Z2, that complex number there. OB is Z2, because it said that up there. Let Z1 and Z2 be represented by vector OA and OB respectively. Okay. Now it says show that Z3 equals Z1 times Z2 and that the vector OM equals the product of Z1 and Z2. We're going to have to look at modulus and we're going to have to look at arguments to do this. Okay, now we know that triangle OBM is similar to triangle OIA. So if we know that, I'm going to do ratio because I constructed them to be similar. Okay, so therefore I can say, for example, that OM, what's its corresponding side? OM over OA is equal to, I don't want it to be doing BM and that because I don't really know much about it, OB over OI. Now, let's do them. Now, OM, the length of OM, isn't that the modulus of Z3? Over OA is the modulus of Z1, that's its length modulus, equals OB is modulus of Z2, over OI, what's the length of OI? 1. Okay, so therefore, from that, where will I work? I'm moving over here now, so I'm going to do it in 2 parts. So therefore, I'm going to cross multiply. The modulus of Z3 equals the modulus of Z2 times the modulus of Z1. Now, so therefore, the modulus of Z3 equals, now back in the first exercise, I think you did modulus of Z1 times modulus of Z2 equals the modulus of Z1 times Z2, okay? Equals modulus of Z1 times modulus of Z2. Okay? Remember, if you're trying to show that Z3 equals Z1, Z2, and vector OM represents the product of Z1 times Z2, we've got to prove that the moduli are equal and that the arguments are equal. So now we need to look at the angles. Okay? So we've just proved that the moduli of the modulus of Z3 equals the modulus of Z1 times modulus of Z2. Yes.
How did you know where to put the
I had to draw, because I've drawn sort of like an obtuse angle here, I just drew this. It doesn't matter if it's straight up, probably not straight up, it'd be a little bit slanted, just to make it roughly the same size angle as that.
So just based on the judgment that
Yeah, just the judgment. Yeah, it's not directly above it or anything like that. Now, let's look at some angles. See, this is the angle for, we can see angle OAI, that equals angle MOB, because that's how we drew it. So angle MOB equals angle AOI. So that angle equals that angle, which is equal to, now, how do you work out this angle? Isn't it just the argument? Isn't it whatever that angle is minus this angle? Does that, so this angle in here, let's say all of that was 70 and this bottom was 50, that would be 20. So it's just the argument of Z3 minus the argument of Z2. Now that difference actually equals the argument of Z1. Now, I'll show you again. How? Because we drew it that way. I purposefully drew, they're similar triangles, I purposefully drew this angle the same size as that. How do we, this angle is just Z1, arc of Z1. This angle is the arc of Z3 minus the arc of Z2. Okay? So therefore, angle MOB equals angle AOI. How do you work out angle MOB? It's the argument of Z3 minus the argument of Z2. It's that angle minus that one. And we know that the argument of Z1 is just this angle. So therefore, the argument of Z3 equals the argument. So if I take the arc Z2 to the other side, therefore the argument of Z3 equals the argument of Z1 plus the argument of Z2. Does that make sense? I'm just taking minus arc Z2 to the other side to make it plus arc Z2, just like algebra, solving an equation, right? Which equals, what's the rule? Argument of Z1 times Z2. So therefore, now that the modulus for Z3 equals the modulus, no, argument of something times something else, I give you this, you write that. We're doing it in reverse. Yeah? Okay? So therefore, my complex number Z3 is equal to Z1 times Z2. How do I know? That the argument of 3 is equal to the argument of Z1 times Z2, and the modulus of Z3 equals the modulus of Z1 times Z2. So therefore, Z3 equals Z1 times Z2, because it's the modulus of Z3 equals the modulus of Z1 times Z2, and the argument of Z3 equals the argument of Z1 times Z2, of Z1, Z2. And therefore, OM represents, therefore, Z1 times Z2.